Okay, let's take a look at scientific notation, which is using exponentials to make handling very large and very small numbers much easier. In electrical and electronic fields, you will find both very small and very large quantities. It's common to have electrical current values of only a few thousandths or even millionths of an ampere. So we're dealing with values of current that are at 0.001 or 0.000001 values. Well, all those leading values of zero become a pain to work with. They might be easy to enter in your calculator, but sometimes on paper it's easier if we can handle them using scientific notation. You'll also find resistance values ranging up to several thousandths or several million ohms. So scientific notation provides a convenient method to express large and small numbers and to perform calculations involving such numbers. In scientific notation, a quantity is expressed as a product of a number between 1 and 10 and a power of 10. So if we look at the example here, 150,000 can be quickly put into scientific notation by noting the number of places to adjust a value between 1 and 10, and we end up with 1.5 or 1.5 times 10 to the 5th. Sometimes that 10 to the 5th can be easily manipulated out of an expression and made a lot easier, especially in a quotient or a product. In the second value, where we have 0.00022, you can see we moved the decimal point now 4 places to the right, and we have a negative exponent. So here we had a positive exponent by moving the decimal point 1, 2, 3, 4, 5. Actually, 1, 2, 3, 4, 5. To 1.5 and to the left, and then in the second one, 4 to the right. Convenient methods then to express large and small numbers that can be done using our exponential values. The exponent indicates the number of places that the decimal point is moved to the right or left to produce the decimal number. Okay, so if we look at the example here where we have 6 zeros, we can call it 10 to the 6th. 5 zeros, 10 to the 5th, and so on down to no zeros, 10 to the 0 power, and it becomes 1. So any number to the 0 power is 1. On the other side, where we have decimal equivalents, then we have a decimal point place that we would move 1, 2, 3, 4, 5, 6 to make it 10 to the minus 6. Okay, and so on down to 10 to the minus 1. So again, what we're going to see is that this helps us to handle very large and very small numbers in our mathematical analysis. If the exponent is positive, then, and we want to open it back up and make it a full decimal number, 10 to the 4th becomes 1 times 10 to the 4th, which is telling you to add 4 zeros. If the exponent is negative, 10 to the minus 4th, 1 times 10 to the minus 4th is telling you now to add those same 4 zeros, but moving in the opposite direction. Okay, so we're moving them right, we're moving them left. So if we look at examples here, expressing each number in scientific notation, your text gives you 1, 2, 3, 4 values here that you are to convert into scientific notation. So 200 becomes 2 times 10 squared. 5,000 becomes 5 times 10 cubed. 85,000 becomes 8.5. Again, remember the rule, 1 and 10. 8.5 times 10 to the 4th. And 3 million then becomes 3 times 10 to the 6th. And later we're going to find out that we're going to use values of metrics to replace these exponentials of 10 to the 3rd and 10 to the 6th. And we're going to see that we can handle those metrics just like it was a number. Another example here, we've got 2 tenths, 5 thousandths, 63 ten thousandths, and 15 hundred thousandths. Okay, so we're going to convert each of these decimals then into a metric. 2/10 becomes 2 times 10 to the minus 1. 0.005 becomes 10 to the minus 3. This becomes 6.3 times 10 to the minus 4. And 1.5 times 10 to the minus 5. So it takes a little bit of practice. You just have to look and remember which way you're moving the decimal point in order to do those conversions. Okay, in the next set, we're looking at a product here of values times an exponential. So 1 times 10 to the 5th, 2 times 10 to the 10 cubed, 3.2 times 10 to the minus 2, 2.50 times 10 to the minus 6. And keep in mind later, as we start doing accuracies and significant digits, that 0 has meaning, so you have to keep track of it. So we move the decimal point to the right or left the number of places. So in this case, it actually just becomes 10 to the 5th, which is 100,000. And the second one, we have 2 times 10 to the 3rd. So 10 to the 3rd is 1,000 times 2 gives us 2,000. In this case, 3.2 times 10 to the minus 2 is really just telling us to move the decimal point 2 places, 1, 2, to give us our result. And then 2.5, the same thing here. We're going to move the decimal point 6 places to the left to come up with our decimal equivalent. Okay, another example here. In addition, we're going to express the numbers to be added in the same power of 10, adding the numbers without powers of 10 to get their sum, and then bring down the common power of 10, which is a power of 10 of the sum. So if we're going to add together 2 times 10 to the 6th and add 5 times 10 to the 7th together, we need to express the result in scientific notation. So the first thing we do is express both numbers in the same power. So in this case, let's leave the first term alone, 2 times 10 to the 6th, but let's adjust 5 times 10 to the 7th by adding a 0 and reducing the exponent by 1, so that we have, in this case, both of them as 10 to the 6th. So in this case, the 10 to the 6th remain common. Now all we have to do is add the leading term, the 2, and the 50 together, and we come up with 52. So now we have a sum of 52 times a product of 10 to the 6th. Okay, the sum of 52 times 10 to the 6th, again turning into scientific notation. Between 1 and 10, we move the decimal point over 1 place to the left, and we have 5.2 times 10 to the 7th. Okay, they give you a related problem. I'll let you work that out. Subtraction, the same thing. We're going to take the two terms, 2.5 times 10 to the minus 12th, 7.5 times 10 to the minus 11th. We're going to get the exponents the same. It's kind of like our common denominators that we've learned here. In this case, we're coming up with a common exponent. So we're going to take the first term and we're going to subtract it from the second term. Okay, so we have 7.5 times 10 to the minus 11th. That term remained. We're going to move the decimal place on the first term to make it 0.25 times 10 to the minus 11th. Now we can subtract 0.25 from 7.5, and we get 7.25 or 7.25. Again, that becomes a product times 10 to the minus 11th. And in this case, since it's already set up between 1 and 10, we don't have to do anything with it. We have 7.25 times 10 to the minus 11th. Again, your text gives you a related problem for you to work out. In multiplication, where we have a term 5 times 10 to the 12th, 3 times 10 to the minus 6, we handle a little differently. Now, what we're going to do is gather terms. We're going to gather our leading terms, 5 and 3, and multiply them. And then we are going to gather the exponents. Again, if you don't remember how to do this, go back and relearn how to handle exponents. It simply becomes a matter of adding and subtracting. So 5 times 3 times 10 to the 12th minus 6. Okay, so we're going to subtract, and we end up with 15, 5 times 3, and then the difference in 12 and 6 gives us 6. In this case, again, we need to adjust the decimal point one place to the left so that we have a scientific notation. We end up with 1.5 times 7. As a quotient then, dealing with division, we're given an example of 5.0 times 10 to the 8th. We're going to divide it by 2.5, 2.5 times 10 to the 3rd. So if we set it up in our common form here, put the numerator as 5.0 times 10 to the 8th, put the denominator as 2.5 times 10 to the 3rd, we can actually start looking at, well, what can we do to the exponential portion? Well, you learned in ET111 or in your other associated math class that I can take the exponent, move it into the numerator, and subtract. So 2.5 goes into 5 2 times. 10 times 8, 10 to the 8th minus 3 gives me 10 to the 5th. When we're done, we actually have a scientific notation form, 2 times 10 to the 5th. Okay, so in the next section, we're going to look at something that is really a subset of scientific notation, and it's called engineering notation and using metric prefixes.